Rudolf Hanel, or Rudy informally, to the Complex System Center virtually. So Rudolf has a position in Medical University of Vienna and simultaneously Complexes Science Hub in Vienna. And he's been working in the field of complex systems since 2007. He finished his PhD in '99 in theoretical physics. I'm not entirely sure which part of theoretical physics, but I suspect statistical physics.
It was field theory. Sorry.
Field theory. Oh, okay. Oh, that is well, field theory and statistical physics. That is also an option. Statistical field theory. Anyhow, well, so he has basically worked all over the place. I mean, not physically per se, but I mean, so subject-wise, statistical physics, robotics, medical imaging, complex systems, and evolution. And right now, he's interested in understanding non-equilibrium processes, their thermodynamic properties, and associated phase transitions. It sounds very statistical physics. All right, non-equilibrium statistical physics. Well, with this short introduction, let me give the floor to Rudy, and I'm sure he will tell us an exciting story. Rudy.
Thank you, Deb. With this talk, I also will satisfy my own vanity a little bit and tell you about, let's say, the story how we got to be interested into matters of regulatory networks and what we can learn using scaling arguments there. And in fact, as it turns out, we started to become interested in regulatory networks around 2006, when these first PCR experiments, PCR started to boom, and one got data sets from, let's say, 150 genes, where then each individual gene was overexpressed or knocked out, and then you could, and then for each of these genes in relative cells, one could see how they reacted to that. And so at that time, several groups tried to come up with regulatory gene network reconstruction algorithms, but it became clear very soon that that the predictions that we could make were extremely bad. But these were not only our group, so it was generally what one learned is that the improvement to pure guessing was very narrow. So in this case, so even to get some semblance of a network that could be useful in this context, purely from the data driven position, one would have to incorporate prior information like assumptions on the connectivity of the network and so forth. So, because otherwise, results were really, let's say, close to water. Yeah? So they were very thin. And then now basically we gave the thing up for several years, and now we become interested in it again, because it's now beginning with single cell sequencing. We are getting to the point where data becomes rich enough that one can really pick up these ideas again and say, okay, maybe let's give it another try. How much can we learn from a data-driven aspect here now? And most of all, because data appears now that is time dependent. So we get time dependent information, and once we get time dependent information, and not just let's say information from the linear response regime, which, as we see later, is maybe we will see later now why this is completely insufficient, this type of data, to infer a lot about a regulatory network. So this being said, I will jump into the story now. And so from where we start now is the problem which I would call the curse of complexity, which basically is the curse of high dimensionality. And that is, for instance, last year the complete conundrum of C. elegans has been exactly mapped out. And of course, some groups have tried to see what happens now if we simulate. C. elegans is a model organism where actually we know that each cell of the body of this organism. So if we have two individuals, they are completely the same with respect to how the cells form and how they evolve from the egg. So this is why this is a quite interesting organism. We know all the neuronal connections now and so forth. But if one puts that, we didn't do that ourselves, but other people did. But if you put that into a computer, it seems that the model we get does not at all reproduce anything that we would expect from a living worm. So there's this gap between what we already know about the system and what we can actually infer from it. And this being said, how do we deal with that? What is the system? So this is the question here. If we map out the neural connections, is this sufficient? Is this sufficient? Because there's probably a lot of information going through pathways that may not be included or may not be visible at this point. So we are dealing basically with a situation that we have large regulatory networks, and we only know a part of it, and we are quite ignorant about lots of details. If one studies, for instance, molecular microbiological aspects of chemical processes, then one can go down into details as far as you want to. So the complexity never stops. It's always more complicated, as one might suppose from once we have reduced an image to a network. So basically, it's the following problem that we see with the bridges of Königsberg example. So I'd like to take this at this point, because if we take a network perspective, what we do is that we take a quite complex situation, like a town in this case, and then through concentrating on particular aspects of the system, we create a description which we can grasp in terms of networks. But if we, for instance, look at gene regulatory networks, then what does it mean if we have a network of genes? There's tons of processes that link one node with another that now actually represent the link here. And this problem cannot be avoided. And it also cannot be avoided that sometimes we probably simply don't know about interaction that might be relevant. And I mean, history is full of it. I think one example I like here is, for instance, that the chemist who has invented the fluorocarbon hydrates actually invented them for creating a non-poisonous refrigerant, because refrigerants at this time were very poisonous, and he wanted to do something good. But then industry came, and we filled them into gas cans and sprayed them because it's not poisonous. Very, very nice. And a few years later, we have an ozone hole. So if we so our knowledge of the system cannot guarantee that we miss something, and prediction becomes something very, very difficult. And anyhow, already the notion of system becomes quite a difficult thing, because we are now caught in between how the situation really is, which is something that we do not know. We always act out of a position of ignorance, actually, and have to bootstrap ourselves out by doing experiments. And where we often get trapped here is what has been called the fallacy of unjustified concreteness, that once we have created an image of a situation, then we are often easily fooled into believing that what we have mapped out here now is actually now a representation of the underlying reality, and this may only be true to some extent. And so asking questions like what can we mean when we say we know the regulatory system, or what can we mean when we say we understand the system, or what can we mean when we predict the system, are very different things, and they would need to be discussed in separately, but we will mainly concentrate a little bit on the last one. What can we predict about the behavior of a system, despite all the things that we do not know? And one way out of this is, can we scale ignorance in some way? Can we, if we have a small system and we don't know many things about them, or about this system, about how interactions are connected with one another, how the agents of the system are connected and interact with one another, and what can we learn if we scale up the same ignorance, our ignorance about the system, by scaling up the system? And how do we do that? Basically, the basic idea behind that is that we render our ignorance for random structures. And this is what random matrix theory is about. So we say, okay, we have here a system where we don't know how the interactions look, but if we assume that they look random, then we still can say something. And this is a strategy that worked very well for Wigner, for instance, with the well-known Wigner semicircle law, and something very similar has been observed in biology by Robert May, who passed away this year, unfortunately, who also introduced random matrix theory to understand the connection between complexity and stability of a system. And this is basically what we are going to talk about now. But before we get there, just a little overview about methods that are dealing with ignorance. So actually, one could say that most of my work is dealing with the notion of ignorance as E.T. Jaynes uses it. So what is our state of ignorance, and how does the information that we collect allow us to change our state of ignorance to something else? And there are basically two approaches to that, and that is entropy as so in the statistical physics part of the world, we would talk about entropy, and this is something we are also very much interested in. And here, in the case of regulatory networks, these are random matrices. When it comes to that, even in microbiology, we already, even if we look at cellular organisms, we run into another problem, that it's actually quite hard to delineate the system that we need to understand by looking at the object of interest. So if we, for instance, think that we can understand the behavior of a cell by looking at its genome, then this is again only partly true, because many organisms, as we know, decide their fate. So there are organisms that follow cell fate. So there's a fixed program, and like in C. elegans, from the beginning on, it is clear which cell will become what. in most organisms, in most higher organisms, this is not the case. So the cells actually, they communicate in order to find out who they should become. So actually, we get into this problem that the delineation of the system is not even quite clear. So if, for instance, we would like to understand the differentiation process of a certain cell at a particular part of the development of an organism, then we cannot really infer that, we cannot really assume that all the information we need to understand this is contained in the genetic profiles of the cells we measure, because it's actually requiring a community of cells already. So this is one of the problems. Then let's make a short excursion into thermodynamics, because I think it is quite, there's two notions that have been maybe of interest here, because they probably pose constraints on the systems in terms of metabolism, which we have not even tackled now, and will not tackle later, but we just want to mention it because I think it is quite necessary to point that out. And one of the things that we would like to point out is that it's quite, I think, quite necessary to, and that is one thing that we do here at our institute, is we try to develop our understanding of non-equilibrium thermodynamics. And we see, for instance, that let's say the naive reversible thermodynamic terms that we have typically learn in statistical physics courses at the university will not really suffice to deal with the system, because reversible processes act very slowly, while biology, I mean, we act at the finite time scale, and this means that our motors, our biological motors, operate at a finite time scale. And what does this mean? Basically, it means that and what one has to say here is that actually one can show that the amount of irreversible work, so of work that we lose irreversibly by operating a machine, times the time that we take to run through a thermodynamic cycle is actually larger than an action constant, which is specific for this process. This is actually one of my most recent works, and together with Peter Jispa. And what we get naturally here is that there is a position where the system operates of maximum power, where the ideal efficiency drops of the system, the energy efficiency drops with increasing speed, while the power output actually increases with the speed of the engine, as of the speed we run through the cycle. And there's some part where there's an optimum, and there's another part where the power output is actually zero. This is what is called by engineers the idle speed. This is the speed of your drilling machine when you don't drill but just switch it on. This is where all the work, all the power the system uses is actually just put into running the machine, while there's no exterior load. And this becomes interesting because at the global scale, basically we can say that let's say the largest regulatory system that at some point we could realistically try to understand is the whole globe as a system. And here we actually are in the situation that we could interpret this thing as a thermodynamic engine running at idle speed, because there's no exterior load. That all the work that is done irreversibly in in the system, to run the system. And it's quite different for organisms. So if we zoom in now and look at some organism, here again, C. elegans, then there is the idea that these organisms, and this is partly true for molecular motors, actually work close to this maximum power output that can be achieved. So they are, at the moment, we just think of these things as evolutionary forces, as evolutionary pressures that drives evolution into some direction. And in fact, and this is, we believe that this is important because if we look at the evolution of the universe, we see this emergence of structure, and this emergence of structure is only understandable in non-equilibrium situations, for in intrinsically open non-equilibrium systems. And let's say, and here we can make now contact to regulatory systems, because if we now think of our global system now simply as this thermodynamic machine running at idle speed, we can actually use a relation that has been suggested already quite some decades ago. A similar one, not in this particular context, but as a very simple model of non-equilibrium, where we have now an influx of energy, and here we have actually a thermal transaction coefficient. Here we would have the non-equilibrium temperature of the system, and here the heat bath. So if we would think of Earth as such a system, then the heat bath would basically be the background, 3 Kelvin background radiation of the universe, and this would be our ambient temperatures of around 300 degrees. This would be, so we would have this constant influx of energy. These are called actually flux systems, is one of the words that has been used for them. And it is known that in these systems that are actually working irreversibly in between two reservoirs, are actually able to reduce their entropy, which also has been already suggested at some time. Now, just think of the problem that we are now manifestly facing today, is that actually this heat transfer coefficient here is depending on the state of the system. So in our case, it would be this CO2 concentration in the atmosphere. This would be part of this state function, which now would influence this coefficient. And if we could put this together, we actually now have a system with a feedback loop, and we can expect non-trivial behavior from them. But this is only what we get when we look at the largest scale. But if we would zoom in now, we would have to zoom in onto this scale factors. So there is a lot to be learned from the thermodynamic sides, and actually one can extend entropy concepts to non-equilibrium systems. And the only thing is that entropy, we get something more complicated, which I don't have just the probability, the visiting probability of a particle or of the system to different energy levels that it can assume, but we also would have to look at another probability, and this probability describes how the system interacts with its ambient, or how this system interacts with its supersystem. And this is happening with the second probability here, that would actually determine whether now at this point the system receives a driving event from the hot reservoir, or whether it can relax and release energy to the cold reservoir. So, and what happens is that additionally to the classical equilibrium part, we get additional terms which very much look like dissipative heat and dissipative work, and this is where we are here. And now we would like to connect to something else, namely the story of Robert May, who started to introduce random matrix theory into biology and to understand what is called the complexity stability problem. And actually he noted that in the 70s, 80s, one believed that there's a relatively that more complexity means more stability, and this is only partly true. I just look at my time. Okay. And why is it only partly true? It's then true if the additional complexity is in fact redundancy, but it's not true in general. So and to which extent it is true, we can now try to understand using random matrix theory. And this is now where we come to the scaling part of the whole thing, and where we can also understand how we can use our ignorance and scale our ignorance and still learn something from that, is by looking at differential equation models for large regulatory systems. And what is now the problem here, and why things become so incredibly difficult, is that we are now facing a high dimensional problem. The problem is nonlinear, and we will quickly see that we cannot escape it to be nonlinear, and it's stochastic. So we have three things that make life for a theoretician quite difficult in many cases. And especially the first two things indicate that the systems can become chaotic. But more importantly, before they become chaotic, they also can exhibit a lot of attractors. And this is actually working well together with the idea that, for instance, we have one cell, we have one regulatory system, one genetic regulatory system. But the same cells, the same system can be used to work as a neuron. It can be used to work as a muscle cell, a epithelial cell, or whatnot. So we have this analogy between cell differentiation here, for instance, and different attractors of a dynamical system. But if the system we are looking at, the regulatory system, is a society, things are not so much different. So it's always the same thing. So May said random matrices, and what we did at some point is we took this idea and we plugged it, and by actually just sampling a lot of random, by creating examples of them and dynamical systems, and how did we basically, how can one approach that? Basically, by thinking now, here we have our non-differential equation, which, let's say, governs the evolution of a system. We expand it. We make a linear expansion. Expansion at the second order, we actually could incorporate quite a lot of processes. But let's just stick with the catalytic ones, where we have catalysts or suppressors which actually can produce or can enhance or suppress the production of other processes. So let's say this is gene activity, and if gene J gets active, then if I and J have a connection, a positive one, then J can, for instance, positively influence the production of I. One thing that we have to notice, nonetheless, is that activities or abundances are non-negative variables. So it does not, negative activity does not make sense, and neither does a negative abundance. And this alone is actually making systems nonlinear. Why? Because if the linear trajectory would now actually force a system or a trajectory, abundance to get negative, it stopped there. And what does this mean? This means that a part of the system is switching off, a part of the system is kept at zero, while another part of the system still is in the game and operate. And this, they can only come back if they're allowed to, if X point gets positive again, because as long as it's negative, it cannot be reproduced. And actually, by these two conditions, we can now, because the ones that if we look back at this equation, X dot, the fixed point would be zero, but the ones that are switched off could also be negative, and this actually allows us to find all the fixed points of a system, and they are typically, one can make an argument, around 2. No matter how large the system is, the number of fixed points will be very limited. This is different with the limit cycles. The limit cycles of a system, which actually always include this switching, so if they have to go through various so what happens is that always substance has to switch off, agents have to switch off and on in order to get to limit cycles, but the number of limit cycles grows exponentially, basically exponentially with the system size. Well, now to understand the emergence of the instability of growing systems, we can now look at random matrices. And where is a random matrix? A random matrix is here. It's this interaction matrix. And now we assume that the only thing that we know about the system is its connectivity, and let's say the connectivity is K. And we assume that the weights on the non-zero links of the system are drawn from a Gaussian distribution, but it actually does not matter as much. It could be plus minus 1. It can be a different distribution as long as it's symmetric, and even that does only partly matter. And what we see is Kirchhoff's law. So if we look at the spectrum of the eigenvalue spectrum of this interaction matrix, then we see that all its eigenvalues are distributed on the imaginary plane. And Kirchhoff's law is typically stated for a fully connected network, and so therefore the law is that the radius goes with the square root of the matrix size. But if one looks more closely and makes the experiment, then one sees that it actually does not go with the system size, it goes with the connectivity. So the radius of Kirchhoff's, the Kirchhoff radius of the spectral radius of the matrix, of the random matrix, is determined by the connectivity and not by the size of the matrix. And here one sees this is actually quite spot on, and if one gets larger, this coefficient gets closer to 1. This one we can ignore, it's the mean square radius, but it also goes like a square root, so quite nicely. Anyhow, so in order to understand now where instability comes from, it comes from, now we need another thing, we need the decay rate. Because what does the decay rate do? So if we have now the production rates, which are now here in this circle, we can shift this spectrum in the imaginary plane with the decay rates. And if the decay rates are large enough, the whole spectrum is on the negative real axis. And so it's on the negative real parts, and real parts are all negative. And what do we know? If the maximum real part of the eigenvalue is negative, then the system is stable. And there's a fine criterion now that we can see that once, if the decay rates match the Kirchhoff radius, then the first real parts of eigenvalues start to get positive, and this means that the system starts to become unstable. However, this instability always causes at least one species to become zero too. And this means that a part of the network starts to switch off once this happens. And this has a consequence, because now the dynamics is not governed anymore by the original interaction matrix, but only by a submatrix. And this submatrix has a new set of eigenvalues, and it has a new set of eigenvectors. And we see now how a system, this even for smaller decay rates than the Kirchhoff radius, can remain stable, and this is simply by switching off part of the system. And actually, and by switching off part of the system, and by assuming that the active links that are still around are proportional to the relative fraction of the system that is still active, then then we can actually see that. First of all, here, what we did here now, let's go back. So we have here now a system, and now the only thing that we control is the decay rates. So we vary the decay rates from a large decay rate to smaller decay rates and see what happens. And what happens is that, and then we simulate the system, we measure its Lyapunov exponent, and this is what we do here. So here we see the Lyapunov exponent, and if the decay rates are large, here we have an N200 system, K is connectivity 40. So we lower the decay rates, and the Lyapunov exponents get closer to 0. And now here we are at the Kirchhoff radius, and what happens is that now the system switches off more and more of its components, thereby being close to this Lyapunov 0 range, which is often called the edge of chaos. And when half of the system has switched off, and we don't yet fully understand while it's always around 1/2 of the system size, the system cannot maintain stability in this way anymore, and it has to become completely unstable. So if there are additional, this means it would grow exponentially here, or if there are additional logistic constraints, this would mean it becomes chaotic. And it seems that life does not like chaos, full-fledged chaos, so it would like to operate probably here. Here it's both adaptable and partly stable. So you can sit on your attractor, but you can relatively easily switch to a neighboring attractor simply by changing the decay rates a little bit. And in fact, if we now try to do the following, we now try to count the number of attractors that we know that the whole system will have an exponential, the number of all attractors in the system will grow exponentially with the system size, but the number of attractors we typically will encounter is something else. So we start here, let's say here, we run the system for a while, and we reach a fixed point. Then we slowly vary the decay rate a little bit downwards, and then we go on until we reach here, and we count the number of times that we really change attractor. Really one attractor is that we have to move from one attractor to the other. And we did some measurements here to systems up to 60. And we actually see that the number of times we switch attractor here, it grows linearly with the system size. So we are now in the situation that actually the size of our phase space roughly is controlled by the connectivity of the network. So the phase space where we can operate in this metastable way is limited, is proportional to the square root of k. However, the number of attractors that we can meet there is proportional to the size of n. And this means that actually the basins of attraction for the attractors become smaller and smaller and smaller. And with the consequence that actually, if we think that now we get some noise from the environment, we have a noisy environment, then the larger the network becomes, the easier it becomes for such disturbances to push a system from one attractor to the next. And the only thing we can do to counteract this is actually to either to increase connectivity, which makes the volume a little bit larger, but this has other problems. And so what we can conclude from that, we will come to our conclusions, but there's definitely a problem here. So there's a problem that if our systems have let's say, connectivities in a bounded range, we cannot make systems arbitrarily large without losing stability. And okay, this is one part, and I have a few minutes, and this just is enough to add another layer of problems on top of that. And this is what happens if we now go away from the catalytic descriptions and really add second order terms to the whole situation, where we have, let's say, or third order terms, where we have cooperative effects. We have now typically chemical reactions have multiple ins and multiple outs. And so, for instance, in a substitution reaction, you would have 2 ins into 2 outs. And if you have this, and for instance, you have now both constructive sets and destructive sets, so then things become even more interesting, and interestingly in a scale invariant way. So if we, let's say, just look at, let's forget about destructive interactions, just constructive interactions with logistic constraints. And then what we see is that if R means the number of constructive pairs that one substance is involved with, so the number of reactions the number of reaction channels it can go into. And let's say we have a system where we know a priori that the maximum number of different species is n. Then we can actually see that if we start out with a randomly chosen set of initial substrate, then there's a phase transition. If this set is too small, we will not go into this phase transition. But we can, if we can make this set large enough, then there's all of a sudden a very brutal, actually a Van der Waals-like transition, where all of a sudden we can now produce everything. And the only thing that limits everything is logistic constraints. So typically we will sit here in this phase transition, try to get up, but logistic constraints will refrain us from, will stop us from actually achieving it. But if we look at the quantities at the axis, we see here now that this is the number of initial substrate diversity, and this is the final substrate diversity. So if we take our initials, and this is relative, so it's relative to the absolute number of species that we can produce. So let's say that the whole system is scale invariant in this case. So these things is a nice thing, but if we add destructive elements, we see that we also get a very, very sharp transition. Let's assume we have a system, everything is keeping itself going. So the production circles are closed, everything works, and now you start to shoot into the system and break links. And then you see that nothing happens, and then there's a point, one link to many. So this is very, very sharp, and the whole system breaks down. And if you put these things together, you can get this type of punctuated equilibrium dynamics we know from systems at all scales, from species evolution over millions of years. We have these phases where biology works stable, and at some point these systems lose their stability, something changes, or just a fluke. If we can, external perturbance like a meteorite crashing or something like that will cause the system to go to a different attractor now. But what is now, I think, the most, what can we learn now from this scaling behavior in the simpler case? We have seen now we get, if we take cooperative effects, we even get phase transitions which make our life complicated. But let's say we are in between, we are in one of these equilibrium patches between the punctuations, then let's say we can still use our linear idea of before. And what do we learn now from the fact that the size of our operational phase space is limited, is controlled by the connectivity, while the number of attractors is with n. And there we made a retrodiction several years ago, where we still did not know a lot about biology. I don't know if I know a lot more today, but then I knew less, was that we said, okay, what needs to happen is that decay rates need to be very, very precisely controlled if we don't want to have cells to spontaneously differentiate into something else. And then we went to the biologists and they told us, we know this since 20 years. This is the ubiquitin proteasome system. And this is basically, proteins are quite stable. So what happens is that cells need to degrade them at a certain rate. And how do they do that? They tag proteins using ubiquitin. This is a particular protein. And once a protein is tagged with ubiquitin, it's transported to the proteasome, and the proteasome destroys the protein again and makes the substrate available for other proteins. So the first prediction we made at that time was, okay, the systems require decay rate control. Complex regulatory systems need tight decay rate control regulation. And this is, as biologists confirmed to us, quite true. It's the ubiquitin system. And moreover, this system is very integral, an integral component of the cell differentiation system. So it really seems that the decay rate control is nicely used by cells in differentiation processes. And there are two more predictions we could make, and which some biologists say we believe it is true, but we don't have really striking evidence for this now, is that suppressors should actually dominate, because if you have too many positive links, then you, on top of the Kirchhoff spectral radius, you get this one positive, what's it called? So if you have a positive matrix, you have one eigenvalue that grows out to the positive side. I just don't remember, my memory leaves me now. And so too many positive links will make the system unstable even earlier. And this is, so we would think that in an evolutionary process, suppressors, there should be at least as many suppressors in a system as there are enhancers. And what we also would suggest, because it's the only way to avoid systems to get too large, is modularity. Because only then modules can keep their n, so relatively small, while keeping k constant, the connectivity constant. So I think, so this is something, and this is something actually we try to learn about now. And if Corona had not come, and much of my energy would have been diverted into studying Corona spreading, I would have liked to present you already some information on this, but unfortunately, this will have to wait for a few more months until this is publishing ready. So this is something we will try. We are trying now to use evolutionary strategies to show that stability, systemic stability, is actually can be interpreted as a evolutionary pressure that shoves systems towards modularity, and this is, I think, what we can learn from scaling here. That regulatory systems, the number of attractors scales with n, but the phase space volume scales with the connectivity. And with this, I will conclude the lecture. And just one outlook where we now try to apply this practically is with single-cell sequencing data. But here we are actually stuck already with very dimensional reduction problems, and but one can already see that if one fine-tunes the dimensional reduction, and the dimensional reduction becomes reasonable, because at a stable position we only need information about these largest eigenvalues here, and so using this information probably will allow us now to learn a little bit more about complex regulatory networks using on the basis of single-cell sequencing data. So this is at least our hopes at the moment. And with that, I will conclude, and thank you for your interest and time, and I'm open to questions. Thank you.
Thank you. Sorry, I was actually looking for the unmute button from the Zoom session. Yeah, these are very interesting issues, the emergence of modularity and evolution in particular network systems. Are there questions? If so, I think the standard procedure is just open your chat button. Let me also do that so that I can see. Yeah, and just raise your hand, and then I will give the quote-unquote floor to you to ask questions. Okay, so far I don't see anything. Yeah, as I was looking at one of these slides when you showed the transition, the age of chaos figure, where you had the positive eigenvalues on the left and the negative eigenvalues on the right, I think just past. And you showed that there are so many attractors. What I was actually wondering about, of course, this is a model system, and in biological systems, very often the functionalities are important. So, in the sense that, well, if switching between one attractor, as you maybe I misunderstood, but I thought you said, well, in this middle part, that's basically where life resides, and because then it can quickly switch from one attractor to the other. While it is true, I started wondering about the functionalities. So, namely, that if the functionality of a cell, for example, changes from one attractor to the other, then it is not that handy for life processes to do so. Could you reflect on that?
I think the observation you make here is exactly the point that I wanted to make in this third part here, the emergence of modularity.
Yeah.
Is that if we look at what biologists learn by doing the hard experiments, is that they really can understand they define these functionalities. They find that for instance, you have this the circadian cycle, which is a very, we know the genes that involved in the circadian cycle, and if we look at these random matrix systems, that one thing that is obvious here is that they always synchronize. This is something I did not mention really, but actually you see that the whole system, if it's on a limit cycle, everything goes with the same frequency, and this is definitely not true for different parts for different modules. I say now in the regulatory system of cells. And actually, this is why I believe that biologists will probably will learn more quickly how cells work by, doing really this kind of experiments, because the cross chatter between these modules must be very, very small, because otherwise these systems would start to synchronize. And if we look at, for instance, the C. elegans case, many of the simpler organisms use this self-fate program kind of building an organism, where the genome is really like a book, and if the mother cell divides, then the daughter cell already gets the book opened at the particular chapter, and it's really, these chapters are separate in a sense, except for the essential machinery, which is the same for all. But I'm suspecting that also in higher organisms you will find this modularity is crucial for establishing stability of the organism, and is actually the only thing that makes me hopeful, why I believe that it is possible to map out these systems, because they need to be understandable in terms of these chunks of this modules, and which in themselves probably have to be very sparsely interconnected. And I believe that this is a chance. So this shows us that there is a chance, because otherwise I would need to get depressive and stop my work here and say, okay, I do something where I believe that at the end of the path there may be results that we can believe in. And I think so. I think this is a very valid and important observation, that nature acts modular, and probably one might learn from that over-connecting a system is not good for its stability, and this is something that maybe humanity can take as a
well, the developmental biologists are certainly quite interested in this thing. Anyway, okay, so thank you and let's see if there are any other questions. Yes, Daniel Oberski has a question. I'm going to switch off my microphone. Please switch on yours.
Thanks, Sepp, and thanks for this very inspiring talk. I'm very unfamiliar with all of this, but I was a little reminded when you spoke of these different basins that start appearing when you grow the N, of the theory of learning neural network models, where we know that if you make them very big and very connected, then it also creates these different basins as well. But there, it's actually considered something positive, because they actually happen to be functionally close to each other and good basins, so to speak. So in a way, I was wondering, I guess, two questions. Is there some connections between these findings and what you were doing? And then secondly, could you also reason the other way from the modularity, that maybe if you grow the N, you get lots of different basins, but they're pretty good ones?
I mean, maybe I would have to learn a little bit more what is going on in neural networks at the moment. I mean, I'm aware to the point that one in this hierarchical deep learning structures, you had the top layer. You also try to use a relatively low dimensional representation space where you map your attractors, basically where you cluster your information. And I'm not saying that the systems a priori want to avoid the closeness of some attractors, and but it would be, but from my perspective, is I think that while in the neural architecture, you actually shape your attractor landscape using your training data set in such a way that the nearness of attractors becomes favorable. So in a way, it would be interesting because we actually are at the beginning of implementing, let's say, evolutionary algorithms to see how evolution acts on the structure of networks and their spectra. If we use system stability as an evolutionary criterion, so if we, let's say, you have if you have many such systems evolving, and you always kick out the ones that get unstable and then replace, let's say, take one of the stable ones, mutate it a little bit and put it back into the pool. So whether this would lead to a similar effect, that we actually get a bunch of that we get attractors close to each other that we like to have close to each other, because neither of them leads you to instability. So I would say that it might be an indication that actually what you are saying is actually maybe an indication for me that evolution really can act that way, that you can get your that your network is shaped in such a way that the way your attractors are posited in your phase space becomes favorable. So thank you. This is an idea that is maybe more useful to me. Is useful to me. Yes, thank you.
Thanks so much. Very interesting.
Any other questions? Okay, well, in that case, let's thank Rudi for giving such a motivating talk. And there are some things that actually touch upon my own interest and own work, which I will pick up with him separately. So Rudi will quite soon get an email from me. And yeah, let me, sorry.
I'm looking forward to.
Okay, right. Yeah, let me also take this opportunity to mention that on November 19th, we have our next talk, and the speaker is Denise Pouma. I hope, I mean, it's a French name, so I'm not sure if I'm pronouncing it right. And she will give a lecture on scaling in urban systems. She's a geographer and a professor at the University of Paris 1, Panthéon-Sorbonne. She specializes in urban and theoretical geography. Her main scientific contributions surround building upon evolutionary theory within urban systems and transferring concepts and models from self-organizing complex systems towards social sciences. Different departure from today's biology-oriented talk. Well, so I hope to see you there, and I'm sure in due time you will hear from Robert and Chinji on the talk on November 19th. Thank you.